couple more minutes.
OK.
And we are live.
Excellent. OK, so my name is Marcel. I'm a software developer, architect with Sechs Wunderkinder, and also have my own company called metaobject. And we just...
Sorry, just go back to...
Hey, yes. OK, we're back. And previously, I worked at a startup called Livescribe in Oakland, at Apple in the performance group, and at BBC. And I'm going to talk about software architecture. Woohoo! Let's see. Yeah, OK. So motivation. Why do I care about software architecture? And of course, the first one is you don't really have a choice, right? If you build software, it has some kind of architecture. And usually, if you don't actually care about the architecture, you will get the default architecture, which is called the big ball of mud. And hence, who has built a big ball of mud? Yeah, right. That's what we usually get. And there's some issues with that, right? And to get to sort of what those issues might be, let's look at real architecture, right? So here we have the big pyramid in Gizeh. And this is, well, it's not a big ball of mud. It's big hunk of stones, right? And we just pile them on top of each other, like we usually do software. And it's about 150 meters high. And they used 7.5 million tons of stone to build this, right? So that's a lot of stones. And here we have the cathedral in Cologne, my hometown. And it's a little higher, 160 meters, and there's a lot more space inside. It's a lot more light, and they used 160,000 tons, right? That's about almost a factor 50 less, right? And what's the difference between these two, right? Did they have different technology? No, both of them were just piling rocks on each other, right? But the arrangement of those rocks was different, right? And the big difference was the arch, right? The Egyptians did not use the arch. I think they knew about it, but they didn't use it for the pyramids, whereas for the cathedral, they used the arch and architecture, right? So that's sort of first level of motivation coming from outside of the field of software. So let's go back to software. And what does it take to build sort of modern personal computing, right? So on the left, we have the Alto from Xerox. That was sort of where they invented personal computing. And it had a graphical UI. It was monochrome. They had networking, invented Ethernet. They had word processing, sort of the precursor to Microsoft Word was built there. And that was about, Alan Kay claims this was about 10,000 lines of code. In the middle, we have Windows, right? It was nicer GUI. Now we have Internet, not just Ethernet. We have big word processing. And that's 100 million lines of code. That's a factor 10,000, but it's nicer, right? So who knows? And then the third one, that's Frank. So the same group, Alan Kay's people, they had an NSF research grant recently, and they said, we should be able to do this better, right? So they built a color GUI with internet, with word processing, programming, all that, and it's less than 100,000 lines of code. So that's still a factor 1,000 less. And their claim is, this was mostly because they use different architecture approaches. So a factor 1,000, now, Windows is better, right? It's more polished, it has more features. But I doubt it has a factor 1,000 better features. And so third motivation, I think this was 1986. There was a challenge by a guy called Bentley, who did programming proles column in the ACM. And he said, I want to see a program that, for a given text, returns the top n words, right? A word count. And so the Obi-Wan of computing, Don Knuth, he came back with his literate programming, Pascal with web, and it's really cool. And it was 12 pages of code. I only show 6. And on the right-hand side, that's Doug McElroy. He invented Unix pipes. And he said, yeah, I can do this in 6 lines of code, because it's Dataflow, right? The other one was procedural, that's Dataflow. 6 lines of code, 12 pages. So, makes a difference, right? So hopefully you're all excited now. You're not asleep anymore. And so I'm going to give you a little overview of what I'm going to talk about. First, we need a little bit of theory. There's components, connectors, configurations, styles, adapters, architectural description languages. And then we're going to look at something that you're not going to find in the literature on architecture, which is sort of all the architectural elements that make Cocoa really cool. And there's a lot of that there, which is really surprising. I'm going to give you a practical example of some architecture applied to Wunderlist, some maybe surprising architecture. And I'm going to finish up with sort of this, what are the special problems in UI software that we have, and most of us, I think, build mostly UI software, that's not really addressed by our tools. And these happen to be, I think, and there's other people who say so, largely architectural. And a lot of that could maybe be solved with linguistic support, if we had that. So that's kind of where we're going. So, architecture, the theory. What is architecture, right? I said something about organizing and then putting stones together and stuff. So it's really, the organization of software in interconnected parts, right? We have our parts and we put them together somehow. That's the architecture. And mostly we have components that we're really familiar with that. That's procedures and objects and programs and stuff like that. And we build these all the time. More in a definition, we have computation and state. That's the components. And then we have connectors, right? How can these things be connected? How can they communicate? How do we structure these components? And the software architecture community says that's the biggie, right? The components, yeah, that's okay. But the connectors are really where the magic is, and where our programming languages today are kind of letting us down, right? Because they usually come with a sort of a fixed set of connectors, and that's it, and you can't do anything about it. And if you need sort of slightly different way of communicating, tough luck. And so when you put the components and the connectors together, you get a configuration. And that can be a system, a program, or a bigger component, and potentially a bigger connector as well. And then you also have styles, which I'm not going to talk about too much. These are essentially types of configurations. So, for example, pipes and filters is a very, very popular style. And they say how you can put things together. So, component. Very simple, computation, storage. It attaches to connectors via ports. Not really a big deal, right? Inside you have components, and you have ports to sort of hook it to the rest of the world. Connector actually looks very similar, except that we say they're not ports, they're roles. And there is actually some research that says you can't really tell the difference if you look really close, but sort of in practice, they're really quite different, because some are used for communication and some are used for computation. And then when you put the two together, you have a configuration. And again, you can also call that a system. And oftentimes, you actually know what the connectors are in detail, because for your style, you're kind of predefined, so you don't really need all that detail, so you just draw an arrow. And then you have your typical architectural diagram, which is boxes and arrows. In order to describe these systems, these configurations, we sometimes have so-called architecture description languages. This is an example of one. It's called Acme. I think it's from CMU. And the system that I want to describe here is essentially a pipe of ls and word count, right? And so I have two components. One is called ls. It has a port, standard in, standard out. Well, it has two ports, the component. Then I have another component. It's called word count, WC. Also has standard in, standard out. And I have a connector. That's a pipe. That has roles. We don't call them ports, we call them roles, whatever. The source and a sink, and then I have to specify how they're put together, right? So the standard out port of the ls component connects to the source of the pipe. The standard in of the word count component connects to the sink of the pipe. And of course, I could have written that all a lot simpler by just ls pipe word count, which is sort of one of the reasons that architecture description languages haven't caught on, right? For example, the precursor to Unix, Multics, it had a syntax very similar to sort of this architecture description language. It had all the features of redirection and pipes, but nobody ever used them. you can see why. It's like, well, I might just put it in a file, and I'm not going to use these pipes. So syntax really does matter. We've talked about that we have components and connectors are really important. So I'm just going to, I can't really give you a sort of overview of the entire field because that's big books, and I don't have 2 days. I only have sort of probably not that much time left. So I'm just going to give you a quick overview of some of the styles that are available. Right? For example, the one that we are probably most familiar with is like call and return. Right? Call a method, call a function. Functional program really is an instance of that particular style. And what's important about that style is when you want a result, right? You must get a result back, and you must get a complete result back. You can't really have partial results, for example, not with a function. Right? You can also not really have no result. You can have void return, but then you can't, not really at the same time. Another example is Dataflow. We talked about the pipes and filters, one of my favorite styles. There's variants of Dataflow. There's, reactive is all the hype now. One-way Dataflow constraints are also an instance of Dataflow. Spreadsheets. Spreadsheets are one-way Dataflow constraints. Implicit invocation, events, that's sort of, UIs have a lot of events. So the mouse moved. User clicked the button. That's an event. It doesn't really have a target, right? You don't really know who that belongs to, unlike a message sent. That has a target. Sorry, I'm flaking. Anyway, data access is another type of connector. You're reading a variable. You're reading a file. You're accessing a database. You're accessing a web server. That's all data access. Messaging could be considered sort of a variant of call and return. It's more flexible, and I'm going to talk more about messaging because I personally think it's a really important style and connector. And of course, one of the big styles that we have these days, sort of since the early 90s, is REST, right? Representational state transfer, and that's the basis of the World Wide Web. And it consists of a very few verbs, unlike, for example, message passing, which you have thousands and millions of verbs. You just have a few verbs and some resources. And it turns out that there were previous attempts at building large distributed systems. There was Xanadu, there was Corba systems. They all failed, and the REST pattern kind of clinched it. Interesting. Architecture really matters. So let's talk about the messaging style. Alan Kay kind of once said that he was really sorry he coined the term object-oriented because it kind of put the emphasis on the wrong thing, which is the objects, which is the components. And he really should have called it messaging, message passing, because that's where the magic is. And he actually used a little Japanese word called ma, which apparently means something like sort of the in-between, the interstitialness. And it turns out that when you have messaging, you can have lots of different variants that can all still be considered messaging that have very different characteristics. So, for example, if you have synchronous messaging, you have Objective-C. If you have asynchronous messaging, you have Erlang, local remote, right? Distributed objects or Erlang remote calls. You can have a straight call, right? Arguments on the stack, and it's just executed, or you can have your message reified, especially if you do remote. You need to reify them, and you can have early bound, C++ style, or procedures, or you can have late bound, and then you have Objective-C. Another very important type of connector are adapters. These take you from one architectural style to a different style. And for example, probably the most common one of these is the Unix standard I/O package, or POSIX. Because you're writing your filters in a procedural style, right? Just C, you're calling functions, you're putting some stuff in a variable. But on the shell side, you're doing data flow, right? And calls to the standard I/O library bridge that gap. right? Arguably, Objective-C itself is also an adapter, right? Because again, like standard I/O, you have sort of C in the middle, but on the outside now you have messaging. And that gives you all this goodness of messaging that we just talked about. And of course, in Cocoa, that flexibility of the messaging part and the Objective-C part was used to do lots and lots of adapters. And let's talk about these. So for example, NSRunLoop is an adapter, right? It takes events, right? Again, mouse moved, mouse was clicked, something happened. And it turns these into messages that are sent through the NS responder chain, right? And so despite the fact that you're dealing with events, you can just code with objects and messages, and you're fine, right? My favorite one is target action. When I first saw this, it just blew my mind, because I can put a button on the screen, right? And I, as the user, when I click the button, I'm sort of in the program sending a message, right? And there's nothing else to be done. It's just, send this message to that object, or find a receiver for that message. And that makes it really, really transparent, because we can deal with this one concept all the time. Again, notification centers, that's implicit invocation. Bindings, right? That's data flow. That's two-way constraints. Perform selector on main thread, perform selector on thread, turns a message and turns it asynchronous, right? And the receiver is the NSRun loop. That's via the NSRun loop, which then acts like an actor. So we have actors. We've had actors since like 1992 or something. And of course, nibs and storyboards happen to be configurations, right? A storyboard, the components are your screens, and the segues are connectors, right? And a nib primarily connects, well, I mean, it does a little bit of layout, but sort of its main function is really to connect all the objects, right? That's what an architectural description language, there we go. That's what an architectural description language does, except this is a visual language, right? And this is kind of made possible by the fact that the way we deal with talking to the UI is via a connector. If it were a callback, we couldn't do it, right? We couldn't do interface builder if it were callback-based or closure-based, because then the nib file would have to contain code. And then either we would have to generate code for the whole thing, or we'd have, when we load the nib at runtime, we would have to, at runtime, compile the code. And also, it's much less visible, because here we can just draw a line, right? And then we know exactly what that means. Which is all very cool, but it's also limiting, right? Because as a graphical language, it has very limited ability to provide abstraction, right? We can't say, like a subclass, well, this nib is just like this other nib, except it's slightly different. Or including nibs, I think it's theoretically possible. In practice, it's very difficult to actually compose nibs together. And if you want to make sort of global changes to a nib, or to a bunch of nibs, yeah, good luck, right? You go into interface builder, and yeah, or you have there are some specialized tools that can handle some bulk modifications. So it would be nice if we had that, right? If we could have an ADL that's code. But of course, when we do the alternative as code, then we are back in standard code. We don't, at that point, have an architectural description language anymore. So that's kind of a problem. OK. Quit unexpectedly. That's useful. Let me...
Some help?
Einfach abgestürzt. And where's the talk about Apple software quality? Is that coming later today? Later today, yeah. Okay. OK. And this is a completely different slide. 16. OK. OK, let's see. Hey, yes, OK. So that was sort of more the theoretical part and a little bit of how that applies to Cocoa. I want to give an example of how we applied sort of architectural principles in Wunderlist. And there was a bunch of different principles that we applied. I don't have that much time. I thought actually when I signed up for the talk that it was an hour. It's half an hour, so it's crunched. And I'm actually only going to talk about in-process REST. The last one, the callback hell, that wasn't intentional. That's one of those anti-patterns. We're trying to fix that. Hexagonal, I don't know if you've heard of it, kind of means that you build your model and you build everything else around it. You don't build on top of external stuff. And of course, we used real MVC, and that solves a lot of problems, rather than Apple MVC, which isn't MVC. So what's in-process REST? A long time ago, actually, at the BBC, building a backend system, I sort of figured out that you can actually take the REST principles, and you don't have to use them in a distributed context. You can actually use the same principles in process, and you get some really nice benefits. And the way you do that is you define something like a URI for inside the process. And those URIs then have some nice properties. For example, they're automatically weak because they're resolved when you actually do the lookup. They can be persisted, right? A pointer is kind of difficult to persist if the object isn't around anymore. They're structured. In this case, we use WL store as the scheme, and then we sort of have an entity type that's like a list or a task or something, and then we have a container. So if you have a task, it lives in a list as its container, and then you have the object ID. Right? And so you can have a URI that refers to a whole set of tasks or to a single task. And you can also do comparisons. For example, you can say, I have one URI here, and I have another URI here, and is the object that the second URI refers to, is that in that list of the first one? And all without actually looking at the object. And the way we use that is we have a central server inside the application, and then it needs to talk to the outside world, right? On one hand, it needs to talk to the UI, and it needs to talk to the backend servers, which may be, of course, we need to work disconnected, and it needs to talk to the persistence store. And all of these need to actually be decoupled, because they're all slower than the central store. So what we have is they're all connected via these URI queues, which use, of course, the URIs that we just defined. And the URI queue is a queue of these references, and it's asynchronous. So we just keep stuffing these things in, and it doesn't matter. We can keep going. And it's obviously persistable because the URIs we put in there were persistable. And it's also, which is, of course, important for being offline, right? If we made a change to a task, and we quit, and we were offline the whole time, we still want that to be sent up to the server when we get back. It's also unique, right? So if we make 10 changes, we only want to send it up once, and we want that to be the most recent one. It's also bucketized. So that's, if we store by bucket, right? So tasks live in lists, and we store the entire list of tasks. And the way we can do that is we just chop off the end of the URI, right? And so if we have 3 tasks that we want to save, and they all live in the same bucket, it'll only get saved once because we're still uniquing. And we can also, when we're going to the UI, right, the UI might not be able to keep up, right? Because we might have 1,000 changes and happening in 2 seconds. And not only can the UI not keep up, but the user can't keep up. There's no point in showing them 2,000 changes. And so we can change that chopping off of the end, and we can chop off more and throttle more, right? And so initially, we might say, yeah, show every single object. But then we say, well, we have 20 single objects, just show the list. And at the end, we can say, well, actually, we don't care. We had so much happening that just refresh everything, right? And it just goes all through this one mechanism. So that was one example, and now I'm going to go back to a little bit more theory. And it's like, this is all hunky-dory, but actually, one of the big things we see with architecture, it shows us what some of the problems are that we have as sort of working developers, right? And one of the big ones is that sort of this reuse thing, right? We've been told that reuse will be magical and great, and it's just not happening, right? And one of the reasons it's not happening is architectural mismatch. And this was a paper written, I think, in 1995, right? And so you would think that yeah, we fixed this by now. Well, in 2009, there was the follow-up paper is, why reuse is still so hard. And really nothing has changed. There are lots of reasons for this, but it turns out that when you go and talk about GUI programming, it's actually worse. And this was a paper I discovered just recently. It's a 2009 paper by a guy called Chatty, Stéphane Chatty, or Chatty or something. It's French. And it has a provocative title, Programs equals Data plus Algorithms plus Architecture, right? Anybody who knows his worth, right, says, oh, well, he's aiming a little high. But actually, he made a little study, and he found out that really there hasn't been that much progress in terms of GUI programming. I think we can all sympathize with that, right? It's too much damn work. It shouldn't be. And he found out, or he says he found out, that actually a lot of the reasons for that are architectural, because the programming languages have an architectural style, usually call and return, roughly, which does not match our programs, our interactive GUI programs, which are more reactive, more passive. And the Cocoa adapters that we've just seen, they help, but only so much. Right? There's only so much they can help. And linguistic support would be really, really great. Now, linguistic support, we just had a new language, right? So it's all going to be good, right? Swift is going to solve it. Except no, right? Because what I've seen so far, and this may change in the future, or I may not understand it well enough, but all the changes I've seen coming from Swift primarily target improvements for algorithmic code. And user interface code is rarely algorithmic. It just isn't. I mean, in Wunderlist, I think I wrote one thing that can qualify as an algorithm. That took a day. We worked on it more than 2 days. And in some sense, I think it's even a step back, right? Because it restricts the dynamic features that made it possible to write all these great adapters that actually made the architecture fit more what we want. And it's kind of pushing that back from that. And I think that's just a real shame. Again, I hope there will be some changes, and we can see what magic will happen. But so far, I'm not really very optimistic. So I've been working on an alternative, which I call Objective-Smalltalk, and it kind of takes the other way around. It says, well, it's primarily an architecture description language, and it can also do algorithms, which fits much more nicely, I think, with what we have to work with as user interface programmers. And when we look at what worked really well with Cocoa, it was this incredible flexibility in the concept of messaging, which is one connector. And the question is, can we extend this flexibility to other connectors? For example, Dataflow, data access, or more Dataflow constraints. And actually, there's some tooling, which I probably don't have time to go into right now. So let's look at what Dataflow could look like. This is an expression in Objective-Smalltalk. Is that? Yeah, I think that's visible. And it defines a pipe, right? So it doesn't compute anything when executed. It just defines a pipe that when you put in a URL on one end, it'll fetch the URL, it'll convert the JSON to a dictionary, it'll then extract one of the elements from the dictionary, it convert to an object, then switch the whole thing to a domain thread, and then run the block that you gave it. And the interesting thing is, it reads really like the diagram, right? It's very similar. And the other interesting thing is, for example, if there's an error, now I didn't put any error handling in here, it kind of goes on to the side, and since it doesn't, it puts its results forward rather than returning. If it doesn't have a result, it just doesn't forward anything. So we don't have to do all this, return an error or the result. Return an error or we don't have to. We just don't forward. And also, what really surprised me when I did this is how easily it managed to switch between threads. It just doesn't really matter, because the logic is in the data flow, not in the control flow. And the threads are tied to the control flow, and the data flow doesn't really care. For data access, we have polymorphic identifiers, which are essentially just URIs in your program. So all of these are really examples of actual things you can write in your program. HTML, the local variable HTML is http://amazon.com. It'll fetch that and put it in there. If you want to save something to a file, again, that's just a simple expression. You have composite references that are integrated into the language, so text field int value, assign that something from the defaults database. Why not? And you have references without strings, right? For example, when we have data flow constraints in Cocoa, we need to switch everything to strings, right? To key value coding, which is kind of awful, right? Because the strings aren't typed, and sort of everything is object for key, this, object for key, that, value for key. Why can't we just write the thing down? And that's kind of then needed to actually deal with something like data flow constraints. So this is an example. I think it's in the reactive Cocoa has this example of a login button, right? When to enable a login button. And this is the almost complete code expressed as a data flow constraint. The strange pipe equals, that's a new connector, and it says that this is not an assignment that happens once, but it's a data flow constraint that should hold always, right? So that means if any of the variables on the right-hand side of that change, the expression is reevaluated. And of course, I just put the actual logic in a separate method, which just checks that the user field is OK, and then that the password and the repeat matches and that they're long enough. And so a little bit more complex example, temperature converter, classic. This is a complete temperature converter with persistence, right? Initial one, that's a normal assignment. You have an instance variable called Celsius. You read that out of the defaults database. Then you specify that you have two text fields, and that they should, that's a bidirectional constraint, so they should always bind to the actual local variables. Then you have two formula with one-way constraints that say how to compute and in either direction. And again, all of this says always true. This should be always true. And then finally, we have a constraint that we write whatever the current value is back to the defaults database. And again, this is what you get as a possibility when you actually make architecture flexible. So that was my talk. I'm not that much over time. And I think that software architecture, these concepts, all these adapters, were actually the key to what made Cocoa such an amazing environment, and still today. It's sad that we haven't really advanced that much beyond it. I certainly can tell you from my personal experience that applying software architecture principle has been the key to whatever little success I've had in my career. But again, many problems just haven't been solved. I think Swift is a step back, and maybe there's ways we can move forward. And that's all I have to say.
Okay. Thank you very much.
Thank you.